want to tell you about sort of three paradoxes. Actually, there's more than three in here, which is, I guess, an extra paradox, but let's not count. So first, I want to talk about a few sort of basics in terms of the sort of systems that we think about as physicists, just to review and get the same language, and then sort of pose these problems that I think both finite and infinite numbers of states can cause. So in physics, we tend to like to talk about closed systems if we can, in the sense that a system is closed if a full specification of the system at some time will tell us the full specification of the system at all other times by some evolution operator. And usually we sort of assume that systems are closed, but know that it's only a convenient approximation, as in George's finitely infinite systems, that there's lots of stuff that is in principle there, but we can neglect in practice, and we can get a very good approximation to what's happening locally. But it's also true that space-time, and in relativity, space-time and causality can create truly closed systems. Physics in some region with a boundary at infinity, or with no boundary, as in the closed Einstein universe, or if there's a null boundary that's incoming, like in this top example. You know, if I want to know if I have data here, I can know everything that's happening up here without any knowledge of what's happening out there, because just by causality, it can't have any effect on what's happening inside. So we can talk about these sorts of closed systems in a sort of in-principle closed way, and then we can talk about open systems that are some sort of subset of a closed system with a time-like boundary, perhaps, in a sort of approximate way. Now, once we have a sort of, say, space-time system like that, we often will talk about the different states that it might be in, often at a particular time. These might be continuous, like particles in a box, classical particles in a box. Or we could discretize them, or we could have a discrete set of particles in a box, you know, not a realistic theory, or just discretize particles in a box, like, you know, setting the unit of phase space to h bar and so on. We can also have phase spaces that are compact, like if we have a bounded energy to our particles, then we can have a compact phase space for them, and they're in a box, or to unrealistically arbitrarily high energy or an infinitely large box, non-compact phase spaces. And when we think about quantum mechanics, we can think of Hilbert spaces that are finite or infinite dimensional. Now, some of these combinations are particularly interesting for purposes of this talk. If we have a finite dimensional Hilbert space or a discrete phase space that is also compact, then we can say that this has a finite maximum entropy, a von Neumann or Gibbs finite or Boltzmann, I guess, finite maximum entropy. Now, this is interesting because there seem in nature to be bounds on entropy that are obeyed by all the physical systems we know about. Bekenstein in 1981 came up with a bound related to the size of a system, its energy, and Boltzmann's and Planck's and the speed of light, constants in the speed of light, that the entropy can't exceed some number. He did this by basically trying to save the second law from black holes. So this is the entropy bound that forbids, that keeps you from kind of making something with super high entropy and dropping it into a black hole, and then decreasing the total entropy, because the increase in black hole entropy didn't compensate for the high entropy of the thing you dropped in. So as long as stuff obeys this bound, you can save the generalized second law of thermodynamics. Now, this suggests that if you take a finite-sized region of finite energy, it has a finite possible number of states, or a finite dimensional Hilbert space, because it has a finite maximum entropy, and it can hold sort of a finite amount of information in information theory. Bousseau posed another version, a sort of similar and related bound, that says that if you take some space-like surface in space-time and draw ingoing light sheets, that there's a bound on the total entropy flux through either the top or bottom light sheets is given by the area of this surface over 4. And this can, in fact, be derived from a sort of version of the Bekenstein bound. And both of these sort of, well, especially this one comes about in some sense because as you try to pack more matter into things, you eventually end up with a black hole, or if you don't, you end up curving space-time in various ways that just tries to enforce this bound. So Flanagan, Morolf, and Wald showed that a version of the Bekenstein bound posed in terms of the energy momentum tensor and a entropy flux, you can then prove Bousseau's bound. But the bottom line of these two is that it seems if we accept these, and these seem to be things that are obeyed by every physical system that people have been able to come up with. So they're sort of like the second law in that people try to come up with ways to violate them and fail, and there's back and forth, and in general these things have survived for a number of years. If we believe them, then it suggests that there really is just a finite number of states that we can pack into some region of finite size and energy. And that's important. Okay, now so suppose either if it's infinite or finite total maximum entropy, we have a closed system. Often we assume these have a nice unitary evolution operator, often that preserves phase space volume like Hamiltonian systems do. Open systems may or may not do this. If we have one of these, say a Hamiltonian system, we have the von Neumann or Gibbs entropy is preserved. Coarse-grained entropy generally increases, and that's a whole system of showing why that happens. And it generally increases or doesn't decrease, but it sometimes does, and there are fluctuation theorems governing that. But I want to talk about now is that if we have a Hamiltonian closed system with finite maximum entropy, then there's a proof, the Poincare theorem proves that if the system lasts long enough, it will eventually return arbitrarily close to the initial state. So for genuinely finite states, a state will recur exactly. If it's a finite maximum entropy, if it's a sort of discretized or if it's a quantum state, it will return arbitrarily close to the initial state. Now, with that in mind, we can start to talk about the first weird situation. I've called this a semi-paradox because I'll get to what really bothers me next. So let's consider a Hamiltonian system that has finite maximum entropy S. It starts away from equilibrium in some macro state A0, and we'll let it evolve. So this is supposed to sort of depict that. Here's entropy, here's the state A0. Entropy increases as usual, and it goes to equilibrium. So we can imagine that our initial state is sort of maybe the universe 13.7 billion years ago, and we're imagining that the universe is some closed system with finite maximum entropy. And this is us now. So now suppose there's some data that's observed at some time. Say we look around in this room. And we'd like to use the data A0, if what we know of the macro state, and what we know of the evolution laws to predict what's going to happen next. Now the problem is that if we then say, OK, let's look at our system and find the instances of our data D, and then see what happens next in a statistical sense, there could be Ds all over the place. There will be D here, there will be D here, there will be D here. And if we look at all of them, we'll see that the overwhelming number of Ds will not be here, but will be in the infinite history of this thing where D comes again and again and again. And almost all of them will be part of fluctuations away from equilibrium, where the system has gone to equilibrium and then fluctuated down a little bit, eventually fluctuated down enough to have a state that can give us data D, and so on. And so there are two tricky things about this. One is that exponentially few of these will be ones in which the system is actually fluctuated down to the sort of entropy we see here. And another way of looking at that is that almost all of the sort of realizations of the data D will be, well, I guess I would say the previous thing, that almost all of them will be realizations that haven't come down this far in entropy. In other words, if we just count up the sort of things that are compatible with D, we're really maximizing entropy subject to the constraints D that we've posed. So for example, we can specify everything that we see about this room and say, OK, what are all the instances in the universe where everything matches what we see in this room? The problem is that if we maximize the entropy of everything just subject to those constraints, the maximum entropy state of this building is not at all what we see or what we saw before we came in here. The maximum entropy state of this building is probably some ultra-hot gas of leptons with some black holes mixed in or something. It's an incredibly inhospitable thing. So if we just conditioned on that and maximize the entropy subject to that data, we would see at the next moment that the doors would implode from the hot gas of stuff coming into the room and so on. So this is simply not giving the right predictions for the universe that we see around us. So either there's something wrong with this argument, or it seems that we do not inhabit a finite entropy Hamiltonian system like this. And this argument has been made by a number of people and goes under the name of the Boltzmann's brain argument. The brain coming from the fact that if you really want to explain the data in this room, you don't actually need the whole room. You just need, my brain with some photons or with some electrical impulses that make me think I'm seeing the room and so on. So the actual maximum entropy thing compatible with some constraints D will probably just be a brain in an otherwise high entropy bath. So this seems crazy. So one conclusion is that this is just the wrong model of the universe. We don't live in that sort of model. Another conclusion is maybe there's something wrong with this argument, but it's really not exactly clear what. Now the thing that really bothers me about this is not this conclusion, because I'm comfortable with us not living in that sort of universe, but this, that the conclusion holds for the entropy of the system being arbitrarily large but finite. So you can pick any entropy maximum for the universe that you like. You can make it, Graham's number that George was talking about, and this conclusion will still hold. But if you make it infinite, then everything's fine. And that really bugs me. If it doesn't bug you, then please let me know what the resolution of that one is. So that's paradox one, that it seems that there is the sub-paradox is that it seems that we can just, by looking around us and waiting for a minute, say something about the global structure of the universe, that it's not a finite maximum entropy system with a Hamiltonian-like evolution. And second, that seems really weird that we can say something about demarcating between an arbitrarily large but finite number of states and an infinite number of states. And no one has explained at all to my satisfaction how that can make sense. OK, so now I'm going to start preparing for paradox number 2. And this has to do, and we've talked about this already now, with statistically uniform infinite spaces. And as I discussed in my first talk, eternal inflation produces these kind of automatically as the reheating surfaces after a bubble forms, or in topological or stochastic eternal inflation, just wherever the field reaches a point where inflation stops and then the universe can reheat. They're generically infinite in the sense that I described last time. Now the properties at a given point on one of those surfaces is determined by the field evolution. And the field evolution is largely classical once you leave, it's got perturbations, the ones that we see in the microwave background, but it's largely classical. With, on top of it, thermal quantum fluctuations, but these have uniform statistical properties. And so what you have is this infinite surface that has the same basic structure, but with uniform statistical fluctuations in it. Now the physical laws that then evolve that early state to, say, now, also obey homogeneity and isotropy. So the later universe is also statistically uniform. Now this is important, I think, because it's not true that if you just have any infinite system and you take a subsystem of it, that will be repeated indefinitely, because you could certainly have a system that just has some funny structure where it's got stuff in the middle and nothing infinitely outside that, and if the stuff in the middle doesn't match your system, then there's no duplication. So to get duplicates, you really need something like a statistical uniformity. But inflation gives you that in a very well-defined way. So the second, now this is a semi-paradox, I would say, is that given a local configuration, we'll have infinitely many replicas distributed uniformly throughout space of it. And that's sort of the argument that we heard from George yesterday, and essentially is that whatever we have here evolved from some initial state. The initial data that led to it is part of a finite state space and should be replicated infinitely often through our statistically uniform space. So our configuration should be elsewhere also. How often it will happen is a very tricky thing to calculate and involves all kinds of subtle questions, but we don't care as long as there are infinitely many of them that will do to pose the sort of paradoxes we're going to think about. And there's no link between the evolution and the cosmic location, where we are in this uniform distribution. So these replicas should arise with a statistically uniform distribution also. So not only are they out there, but we should be able to describe them with sort of the number of Milky Way-like galaxies per unit volume is just some number. That statistical number, that density of Milky Ways, should be constant statistically throughout the universe. So that's weird. So it says there's a copy of this lecture out there. There's a copy of all of you listening to it, except that I'm wearing a pink bow tie, and I'm talking about lectures elsewhere where I have a unicorn horn. So everything is out there, every small variation of it. We would think that some of them would be more or less likely. Probably unicorn horn Anthonys are less probable than non-horned Anthonys because unicorn horns are evolutionarily probably not that useful for humans and so on. But they're out there with some smaller probability. OK, do we care? It's kind of disconcerting, but do we care either personally or sort of from a physics standpoint? Well, I think there's some interesting aspects to this. One is that you can argue as to whether, if you genuinely have an exact duplicate, the exact same quantum state out there, should we be talking about that as a different system or the same system? There's this identity of indiscernibles, philosophical prejudice we might have. It's not clear that that really applies to, say, electrons, but it's not clear also that we should talk about them as different things. We might imagine that since they're sort of actual duplicates, we could reduce this to a sort of periodic universe, but that won't quite work in a naive way because the period will be different for different size things. So replicas of hydrogen atoms will be far more common. I mean, there's lots of them here, than replicas of Earths or galaxies and so on. Second, there are weird, improbable things that happen, like me wearing a pink bow tie, but we can't see or interact with them in any way. We just sort of know they're out there with some tiny probability. Maybe we care about them, maybe we don't. This is very much like the many worlds interpretation of quantum mechanics, where I'm also in some branch of the wave function with a pink bow tie, but with some tiny probability. I've decohered with it in that interpretation, and I can't interact with it. Do I care that it's happening? It's maybe, maybe not. But these two things sort of set the stage for the second paradox, which brings to light, I think, some interesting issues that are related. So the second is, let's now think about doing a quantum mechanical experiment inside some statistically uniform infinite space. So we'll take a single particle spin that can be up or down and give some coefficients to those. And the normal way we can think about quantum measurement naively is to hook those up to an apparatus in the ready state, and then it evolves unitarily to an apparatus up and apparatus down that's a readout. We could also include an environment, human observers, et cetera, along similar lines. Now, the troubling thing comes when we think that from our previous argument, there are replicas of this whole setup. The experiment, maybe the apparatus, the person looking at it, et cetera, distributed throughout space. And we don't know which one we are measuring. So we say, I'm measuring the one right here, but everybody else is saying the same thing. So we can't really say, this is the apparatus being measured. Now this is a sort of aside. The measurement problem, of course, is here. The apparatus that we connected to the system just made the superposition larger. It didn't actually necessarily collapse anything. Decoherence theory will tell us why there can't be any interference between, say, if there's a sufficiently macroscopic apparatus, the up and down states of the apparatus. But then we have to somehow go towards a measurement outcome. Copenhagen and related views would say that at some point we have to replace the superposition with one of its elements. The many worlds interpretation would say that there's always the superposition there, and it just gets bigger and bigger to include, say, the observer that's looking at the apparatus, the environment around the observer, et cetera. Then we can ask, where do probabilities enter? Well, in the Copenhagen-esque versions, I'll call them, there's just a Born rule that we postulate that the probabilities, that the relative frequencies, say, in a repeated sequence of trials are given by alpha squared and beta squared. In the many worlds version, it's somewhat more subtle, and this has bothered me for a long time about the many worlds interpretation, because both happen. You can't just count up how many observers see up and down. You'll always get sort of 50-50 rather than alpha and beta if you just compare numbers of observers. So you have to in some way say that some observers are more real or something than others, looking at it naively, and that's always bothered me. That's all sort of an extended aside. So now let's come back to our system. Our system here on Earth is accompanied by a whole bunch of replicas all over the place. They're very far away. It seems perfectly justified to think of them as independent. So let's just, because we can, consider the tensor product of those quantum systems. And let's consider the wave function that's made up of, say, 3 of them. If we write that out, we get a system that has alpha cubed up, 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 alpha squared, beta, up, up, down, et cetera. It's got all these terms. So now suppose we ask, what is the probability of measuring up? Right? One way to look at it is we can say, OK, let's measure the system. Let's measure this whole thing and say, OK, well, there's an alpha cubed chance that we're in sort of this branch of this full wave function. If we're in that full branch, we definitely measure up. There's an alpha squared beta chance that we're in this one. Then it's a little less clear, but it seems perfectly reasonable to say, well, there's a 2/3 chance then that we'll measure up. Since these are otherwise indistinguishable systems, we could be any one of the 3. So 2/3 up, 1/3 down, et cetera, beta cubed times 0, because there's no probability of being up. And you can do that for n systems and write out what that looks like, where you combine both the quantum probability, these coefficients squared, with the classical probability, that is the fraction of these indistinguishable things which are up versus down. And if you work through that, you get the probability alpha squared alpha back. So all seems fine in the world, and everything seems happy. But there's a slight concern that, there's a feeling that if we know the wave function, we may not know everything about the system. We know we're comfortable in quantum mechanics. We can't predict everything. But we feel like we should be able to predict probabilities at least. And here, rather than just having the wave function come in, we have these classical probabilities. We have sort of a Born rule plus these classical probabilities. And you might think, well, if we're just a little clever, we could come up with a quantum way. We could come up with, say, a projection operator that we could take expectation values of and would spit out these numbers naturally. But that actually you can't do. So Don Page showed that that is, in general, not possible once you have these duplicates to find a projection operator that will give you the right probabilities. So you have to supplement quantum probabilities with classical ones once you admit these duplicates into a quantum system. So whether this bothers you or not, this is just a fact. It bothers some people a lot. And so this got Max Tegmark and I thinking, and David Laser as well, about what do we do with this? And what we found is something interesting. If you just swallow the fact that you have to toss in those classical probabilities, relative frequencies of otherwise identical observers, look at the n goes to infinity limit. So what you get is an infinite sum of infinite sequences. But you can show something very interesting out of that. And this goes back to results from Hartle, I think in 1968, and has been used in some other arguments in similar form. What you find is that you have this infinite sum of strings, and all of them look like a random string of ups and downs, but with relative frequencies of up and down given by alpha squared and beta squared. So a sort of spatial ensemble where the relative frequencies of ups and downs are given by the Born rule. And then there's some terms that don't have this property, but these have a total Hilbert space measure of 0. So if you can say, I'm going to take my wave function for the universe and replace it with a wave function that differs by Hilbert space norm 0, which seems plausible, then what you find is that you have just this sum of things, and every one of them has the same properties. It's a just random collection of ups and downs with the relative frequencies given by the Born rule. So classical probabilities are now doing all the heavy lifting. The Born rule is essentially gone, other than this assumption. Everything is explained by this uncertainty in which of these systems you are. And to me, this puts quantum interpretation in a sort of different light. You've got this infinite set of equally valid observers, so no observers are more real than any other observers now in this point of view. They're all actually there, so this is sort of providing an ensemble for quantum mechanics to be talking about. You can look at two sort of classic lenses of this. You've got this big superposition, but every term of the superposition in the n goes to infinity limit is indistinguishable from every other one. And so you can ask, should we distinguish them if they're indistinguishable, or should we identify them? If you say that they're really indistinguishable, then in the Copenhagen view, you say, well, we had this string of superpositions. It turned into this big infinite sum of this infinite superposition of infinite products. We measure and we pick one out of that infinite sum, but it doesn't matter which one we choose. Every one of them is exactly the same. So the collapse of the wave function becomes totally irrelevant because you're collapsing to any one of the elements of the superposition. Or in the Everett interpretation, they all stick around, but they're totally redundant because every one contains exactly the same thing. The Born rule probabilities are not really relevant. You never have to really square alpha or beta. Well, you never have to use the Born rule. Everything is from these relative spatial frequencies. And randomness in quantum mechanics, in this sense, comes from the inability to self-identify which of these indistinguishable systems doing the quantum experiment you actually are. So this is a lot to swallow. And I give it, so I think this is fun and interesting, but I give it mainly as an illustration of, I guess, what George called an essential use of infinity that I think is really fun and interesting, because it's only in the n goes to infinity limit that the two interesting things happen. One, that the part of the wave function not obeying the Born rule goes strictly to 0. Otherwise, it has, so you can show that it has a norm that is as small as you like. However small you like, you can find a sort of number of systems that gives you that extra piece being smaller than epsilon. But only in the infinity limit does it go to 0, and only in the infinite limit do these truly become indistinguishable. In which case, I think it puts the collapse versus no collapse in a sort of different light, because it simply doesn't matter which one you think about. So that's troubling set of ideas number 2. Troubling set of ideas number 3 is, so let's back up a little bit and think about, there are duplicates of, say, this room. Maybe we care about those, maybe we don't, maybe we want to think about them, maybe we don't. But something we have to think about if we're going out and doing cosmology and doing cosmological measurements is if our observable universe has replicas, we don't really care. If it has near replicas with the same sorts of properties, we don't really care either, because we're sort of used to dealing with that. We can think about variations of our theory and probability distributions of what the observables are given our theory and so on. But what if the properties of the universes, the observable size universes, are not all the same? So for example, you could have some field with some random values that get stretched out by inflation so that within an observable universe, the field is uniform, but it varies over much larger scales. So for example, the axion field could give you different axion densities in different regions, each of which is larger than the observable universe. And that gives you a statistical distribution of axion densities, which you can actually compute. You could also have an inflation. Say you had different sorts of transitions. Even if this is our type of vacuum where we live, it might be that you have different numbers of e-folds of inflation coming from this direction or this direction. So even the same vacuum can have different properties. Or most provocatively, the string theory landscape has all of these hundreds of field directions, and this is a technical term, zillions of vacua. I think we should name 10 to the 500 zillions from now on, just to take ownership of it. As you heard yesterday, and probably will hear more today, the values of these different fields and fluxes determine the sort of low energy effective physics that we see and we would measure in the universe around us. Now, I think what's interesting, there was this analogy with Schrodinger's equation, and it has lots of different solutions, and so string theory has lots of different solutions. But what Schrodinger equation doesn't have in the world that we live in is a mechanism to bring all of those solutions into physical existence, right? They're all sort of theoretical solutions, and there are more than zillions of them. But there's nothing to breathe life into all of those. But in the string theory landscape, all of these vacua have a vacuum energy. Many of them will be positive, and so they drive inflation. If the transitions are relatively slow, they will drive eternal inflation. And eternal inflation will essentially populate all of these vacua. It will bring into being some region of the universe in that vacuum state with those low energy laws of physics. So it poses a lot more interesting problems, I think, when there's a process to actually bring all those mathematical solutions into physical existence, which eternal inflation can do. Now, if that is the case, this raises a kind of problem, because each of these has sort of different initial conditions for the Big Bang. We want to just go out and measure something, like on Thursday, they'll give us some measurements of the microwave background data. And even if we have a theory of cosmology that produces all these different observable universes, which one do we then compare to our observations? How do we do that? Because of this, there are different values for what we could see for the same theory. This question, what values of the observables will we observe, is not a question we can meaningfully ask. That is off the table. There is no answer to that question. We have to say something else like, given that I am a randomly chosen something, so given some set of data, what will I observe? And there are different choices that you could think of for this. What would be observed in a randomly chosen universe by some definition of universe? What values would be seen from a random point in space? What values would be seen by a random observer? This seems suggestive because observations are done by observers. Then assume that our observations are like those of a typical X. This is just a methodological assumption that you would have to make in order to make predictions for something. And then you can compute the probability distribution of observations given that we're a typical X. Now, there are two really difficult problems with this. So if you already don't like this, you're going to like it even less. Problem number one is you might hope that which of these you choose, you get basically the same results. But that is not the case, as I'll say in the next slide. Second is that even if you decide which one to count, it's not clear how to count them. So the first problem is that the choice matters. If you pick, say, universe versus unit volume on reheating surface, those are both valid things you could ask. They give very different answers. One will count, for example, the inflation that happens inside a bubble, which can be things like e to the 60 versus e to the 120 and so on. One doesn't. Okay? So those can be huge differences. Baryons versus galaxies, also things that people have computed things for, can differ greatly depending on whether galaxies form or not. It could be like 0 versus a lot. You can think about things like observers. What is an observer? It's not clear. Other people have proposed observers with our observations, so sort of conditioned on everything that we've seen, everything that we've measured before in cosmology, et cetera. Those will give different results in significant ways. So they don't all give the same results. Some of the choices that you might be attracted to also give strange sort of paradoxical results. These are kind of fun, but troubling. So for example, let's suppose we are typical observers. And let's observe something which is the number of observers who were born before us. Okay? So now we can compare two models of the universe, two models of world history, really. There's this model where we live now, and we solve all global problems, and humanity goes into space and keeps taking over stars and so on. And the population of humans goes up sort of exponentially for a very long time. The other model is the, unfortunately, more realistic one, where we all sort of do something terrible to the Earth in the next 20 years or so. Okay, so these are two models we'd like to look at. Now, in this model, the probability that we're living now, that is the number of observers before us is this big, is really tiny, because a typical observer at a typical time will have a huge number of observers who have lived before them. Versus in this model, it's not so bad. Maybe if we extend this a little farther, we could be sort of at the halfway point. And so some people have said this is an argument why we should expect doomsday to be upon us, because this, given the number of observers we've seen before us, that is much more likely in this model than in this model. Incidentally, even if you believe this argument, I worked it out, we still have a while. It turns out a lot of people were born before us if you actually work out the numbers. If we stabilize our population, we could still last another 400 years or so. But it seems strange that what determines the future of humanity should be this esoteric argument rather than, say, whether we solve global warming or prevent nuclear missiles from going off and so on, right? Which seems much more relevant to whether we're going to survive. An even more suggestive way to put it, so to speak, is called the Adam and Eve paradox. The paradox goes like this. Adam and Eve are in the Garden of Eden, and Adam is sort of telling Eve he'd like to move the relationship to the next level. And Eve says, well, wait a minute, I've heard rumors that there are consequences. They could involve really painful childbirth and so on. I don't think I want to go there. So the serpent comes along and says, well, Eve, you got nothing to worry about, because think about it this way. If you were in fact to have children, your children have children, and so on and so forth, there'd be an exponentially large number of children. What are the chances that you would be the very first two people, right? So it just doesn't make any sense. Much more probable is that nothing will happen, you won't have any children. That makes much more sense, so go ahead, right? And this seems so crazy because it seems like whether Eve gets pregnant or not is very much more a question of biology than this, right? And observing and conditioning on observers and so on. So it may be that these arguments are right, but I think we have to take very seriously that it's confusing, at least, to say that we are typical observers and that we want to use that as a way of reasoning to deduce things about the universe. So that's one problem, that it's not clear what conditionalization object to choose. They give different results. It's not at all clear which one is the right one. The one that seems kind of philosophically most reasonable to condition on the fact that I'm an observer, observers observe things, leads to problems of defining observers and even more thorny problems of Adam and Eve and biology. The other problem is that even if we choose, okay, I want to say an observer is a 10 to the 11 solar mass galaxy with metallicity of 0.1 solar, and so on. So we pick some proxy for an observer. It's still not clear how to count them if the universe is really infinite. And this is a paradox that actually goes back to Galileo. If we have some just infinite set, and we've heard this before, and you're all, I think, familiar with this, then we might say that there are the same number of odd numbers as even numbers, because we can make a one-to-one match between odd numbers and even numbers. But it's also true that we can make a one-to-one match between odd numbers and all integers, or a one-to-one match between integers and then some, we can make any one-to-one match we like. And so it's impossible to say that one sort of infinite set of integers is bigger than the other infinite set. And it seems like, and this is exactly the same sort of thing that happens if we consider red universes and blue universes in eternal inflation. How we line up the red next to the blue universes, we can get any answer we like as to the ratio of reds and blues. Now there's kind of an obvious answer in terms of the integers. You can get an answer to this, which is you say, okay, well, certain integers are next to each other. Let's start at 0, and let's take intervals around 0 and add up the total number of odds and evens within that interval, and then send the interval to infinity. And that will give us a ratio of 1/2. Right? So that's an unambiguous answer that we got by choosing a particular measure that was based on sort of proximity. And we can imagine that something similar would be possible in space-time. Space-time gives us a metric. It gives us a measure of closeness between things. So we would think that we ought to be able to take volume averages, compute some ratio within some volume, send the volume to infinity, and get an unambiguous answer. The problem is that the answer completely depends on the manner in which this is done. And this is a problem that arises because normally when we take volume averages out to some cutoff, what exactly the cutoff surfaces is doing doesn't really matter, because as we send the volume large, the ratio between volume and area gets big, and the area just doesn't matter. That does not happen when we have an exponentially increasing system like in inflation. So this can be illustrated with the following dialogue. This is a real dialogue between me and Alan Guth. Guth, imagine that the universe is made of dominoes, so time is actually running downward here. At each instance, you line up 2 1s with each 2. So this is in some sense meant to be a 2 spawning 2 1s, right? And mocking up eternal inflation. And just repeat that process. Now, at each time, we can cut this with an equal time surface. We see that there are twice as many 1s as 2s. So 1s are twice as probable as 2s. But I say, but you know by construction that each 2 comes with a 1, because these are all dominoes, right? Every 1 comes with a 2. It can only be 50% probability. They must be equal. No, yes. And the problem, of course, is that you can choose your equal time surfaces to run in any way you like. It could be all 1s, all 2s, half 1s and half 2s, etc. There's an ambiguity coming from you saying at some time we're measuring these probabilities. It does not help to say consider everything up to, say, everything above the line and add it all up and then send this line down to infinity, because it's always dominated by the very lowest row, because it's exponentially increasing. So you can't get around this by just running the whole thing for a long time and hoping that the lower edge, where things are confusing, goes away. That never happens in eternal inflation. So this has caused a lot of consternation in the cosmological community, because once you have this eternal inflation or landscape picture, you can't get around the fact that you have to come up with some way of computing probabilities. And whatever way you choose is going to end up involving some sort of comparison between infinite sets. And so you have to do it with some mechanism, generally, that involves a cutoff. There are a lot of choices that people have proposed for how to do this, with some basic philosophies behind them. You could count physical volume or co-moving volume or volume created at some fixed time. That was what we did with the dominoes, and there are various different versions of that depending on what sort of volume you're talking about and what time. So there are all kinds of different choices of what time variable you want to use, scale factor time and co-moving proper time and so on. You could just count up the number of pocket universes in some way, so count sort of these different regions. You can take some world line and count up how many transitions you make from one type of universe to another. You could just try to sort of equally weight everything. So there are all kinds of different things that people have proposed. Now what's interesting is that when you start going through these proposals, you find that one of them may predict that we're a Boltzmann brane. There's also this thing called the Youngness paradox. One I worked out I'll call the fast transition fiasco. There's the Q catastrophe, the up transition upside down. It's the domino dilemma that I talked about, observational obstacles. So things go wrong with many, if not all of these measures. I would say, this may be my limitation, but there is none of these measures that I have understood well enough to even know quite how to apply it, let alone that it's problem-free. And this I'm actually on the fence as to whether this is a good or a bad thing, because in some sense it's bad because it seems like, oh, we don't know what the measure is and they all have these problems. But on the other side, it's much better that lots of them have problems than that they were all perfectly self-consistent, because then we really would not have no way to choose between them. It may be that there are only sort of a reasonably finite number of different sensible ways you can do this, and all but one or two have some serious problem like this. And so then we can more or less converge on some unique solution of how you at least count things, even if you don't know what exactly you're supposed to count. So people in the cosmological community are sort of mixed on how to think of this. More or less every few months there's a new measure which solves the problems of all the old measures, and all the old measures were terrible. Why did anyone ever think of those? And then the process repeats. But it is the case also that it turns out that many of the new measures are the same as the old measures in secret, and it seems that we're sort of running out of measures, and we'll see how that plays out. So I would say that this is a crucial but unsolved problem in cosmology. I think it's not a problem you can avoid if the universe has eternal inflation. This is a problem you have to deal with if you want to make predictions in it. And I think it's a major issue in eternal inflation that there isn't a well-defined and known answer for how to do that. So my summary, I guess, of these three issues is that I would say that either infinitely or finitely many states in our universe creates very uncomfortable issues. So I don't think you get away from these issues by thinking that the universe has finitely many states. The infinite statistically uniform spaces many claim are created by various cosmologies, including me, produce uncomfortable issues. They're neat issues, I think, interesting issues, but uncomfortable ones. The infinite production of different cosmologies with different properties creates uncomfortable issues. My conclusion from this is that maybe we need to get comfortable with discomfort. So one reaction to this is say, oh, this is a lot of bosh. Let's do something different. Cosmology has gone off the deep end. But for me, when I come upon a paradox, I never try to avoid it and just kind of brush it under the rug. To me, it's much more fun to try to sharpen the paradox as much as you can. I find that either the paradox gets resolved and there's something interesting learned, or the paradox doesn't get resolved and I also learned something interesting. So my philosophy is that these are weird and strange and uncomfortable things that are cropping up in physics, but if we keep focus on them a little bit more and think very clearly, I think we may learn a lot of interesting things about the world. Thanks.